Assalamualaikum warahmatullahi wabarakatuh. Good day everyone. My name is Muhammad bin Amir and my metric number is DE250115. I will be introducing our project, a single-phase AC power delivery system for an industrial facility. This project models a multi-source AC grid that combines utility power with backup inverter power to supply inductive loads by bridging steady-state AC mathematics and Thevenin Theorem with Falstad Circuit Simulation. Our team able to analyze every detail. Specifically, we are investigating line independent voltage drop and critical phase shift. The ultimate goal of this design is to ensure stable and reliable industrial power delivery. Now, let's move on to the system parameters.
Hello, my name is FARHAN bin KENALAN, number matrix DE250077. Next, I will explain the system configuration used in this project. The system consists of two AC power source supplying an industrial load through separate transmission line. Source 1 represents the main utility supply with a voltage of 240 volts at a phase angle of 0 degrees, while source 2 represents the backup inverter supply with a voltage of 240 volts at a phase angle of 30 degrees. Each source is connected through a transmission line impedance. Transmission line 1 has an impedance of 4 plus J3 ohms, while transmission line 2 has an impedance of 3 plus J4 ohms. The industrial load selection is option A, which represented a small motor load. The load impedance is 20 plus J30 ohms, indicating that the load is highly inductive. The system operates at a standard frequency of 50 Hz. To simplify the analysis, all resistance and reactance were converted into complex impedance form and then analyzed using Thevenin Theorem before validated using Falstad Circuit Simulator.
Moving on to our frequency domain modeling as shown in the slide, we transition our raw system parameter into phasor form to streamline the complex AC analysis. First, we calculated the impedance representation for the transmission line and the load, converting them into polar form. We also express our two 240 volt sources in both polar and rectangular coordinates, tracking the 30 degree phase shift between them. Next, to prepare for our simulation phase, we calculated the exact physical inductance value needed at our 50 Hz operating frequency. This conversion yield at 9.55 millihenry for line 1, 12.73 millihenry for line 2, and 55.49 millihenry for our inductive load. This mathematical groundwork setup parameter required to simplify the network using Thevenin Theorem.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad IMAN bin AHMAD SAHARUDDIN, metric number DE250080. Okay, now let's look at the analytical method we use. We choose Thevenin's theorem to make our circuit analysis simpler. The original circuit has two power source, which makes it very complex to calculate directly. Okay, by using the Thevenin's theorem, we change it into a simpler Thevenin equivalent circuit. Okay, from our calculations, the Thevenin voltage, which is VTH, is 240 and 695 volts with a 15 degree phase angle. The Thevenin impedance, which is ZTH, is 1.7896 plus J 1.786 ohms. This steps is very important because it helps us calculate the load part easily without doing the hard network analysis twice. Next, let's check the analytical result for the load performance. Okay, using our new simple circuit, we found that the load voltage is 225.21 volts and the load current is 6.246 amperes. The power factor is 0.5547 lagging, which prove that the load is inductive lah. Okay, for the power values, the real power is 780.28 watts. The reactive power is 1170.41 VAR, and the and the apparent power is 1406.68 VA. We will use this number later to check whether our simulation is correct or not. Okay, and then finally for the validation result, here we compare our manual calculation with the software simulation result. As you can see in the table, the difference or error between the two models or methods is extremely small. Every value is below 0.005%. Okay, for example, the error for the low voltage is only 0.0004%, and the power factor error is 0%. This very high accuracy proves that our calculation are correct and our mathematical methods or model is reliable for practical work.
Hi everyone, my name is HAKIM. My metric number is DE250088, and for the next slide is the Falstad simulation model. So I will explain it. So to verify our analytical calculations, we have built the entire single phase AC power delivery system by using the Falstad Circuit Simulator. So in this simulation, we included the two AC voltage sources to represent the main utility supply and the backup inverter supply. Then the transmission line impedances were added to represent the resistance and also the inductance that would normally exist in actual power lines. We also connected an inductive motor load to simulate an industrial facility, because most industrial equipment such as motors and heavy machinery behave as an inductive load. Besides, we also added measurement tools so that we could measure an important parameters such as the load voltage and also the load current. We also used the scope function in Falstad to observe the waveform behavior of the system in real time. So the purpose of using the Falstad is to make sure that our theoretical calculations and analytical results are correct. So instead of only solving equations manually, the simulation allows us to visualize how the system actually behaves in real time. Moving on, this slide shows the voltage and current waveform that we have observed from the Falstad simulation. So as you can see from the graph, we can see that both the voltage and current have sinusoidal forms, which is the normal behavior of an AC power system. So from the graph, you can see that the green waveform represents the voltage, while the yellow waveform representing the current. So one important observation that the current waveform is slightly behind the voltage waveform, or in other words, the current lags the voltage. So this happens because our system uses an inductive load. In an inductive circuit, we know that energy is temporarily stored in the magnetic field before being released back into the circuit. So because of that, the current cannot respond instantly, causing it to lag behind the voltage. So this phase difference also explains why our power factor is lagging and relatively low. Even though there is a phase difference between the voltage and current, the waveform remains smooth and also stable throughout the entire simulations. So this also indicates that the system has successfully reached a steady state operation, in which meaning the circuit is operating normally without any sudden changes or instability. And so overall, the simulation matches our calculations, and we can clearly see how the inductive load affects the system. So this gives us a better understanding of how a real industrial AC power system behaves.
Now, I will briefly discuss the system performance. The inductive load causes the current to lag behind voltage, resulting in a low power factor of 0.5574 and a high reactive power demand. The transmission line impedance also causes a voltage drop, reducing the load voltage from 240 volts to 225.21 volts, which corresponds to a voltage drop of about 6.16%. Due to the inductive load, the voltage and current are separated by a phase angle of 56.31 degrees. This phase difference reduces the efficiency of power transfer. The system delivers 780.28 watts of active power, but also carries a large amount of reactive power, showing that not all supplied power is used effectively. Overall, the system operates successfully, but its low power factor and voltage drop make it less suitable for long-term industrial operation. Therefore, power factor correction and voltage regulation are recommended.
Next, I will present the challenge encountered during our project and the solution we implemented. Our first major challenge was converting the phase angle from degrees to radians. We resolved this through accurate mathematical conversion to ensure our equation align. Second, we faced difficulties configuring the Falstad waveform readings. We overcome this obstacle by carefully adjusting the scope settings until the visual data was clear. Finally, obtaining stable steady-state readings was a challenge. We fixed this through repeated validation and constant double-checking of the circuit. Now, let's conclude our presentation.
Moving on to our frequency domain modeling as shown in the slide, we transition our raw system parameter into Phasor form to streamline the complex AC analysis. First, we calculated the impedance representation for the transmission line and the load, converting them into polar form. We also express our two 240 volt sources in both polar and rectangular coordinates, tracking the 30-degree phase shift between them. Next, to prepare for our simulation phase, we calculated the exact physical inductance value needed at our 50 Hz operating frequency. This conversion yield at 9.55 mH for line 1, 12.73 mH for line 2, and 55.49 mH for our inductive load. This mathematical groundwork setup parameter required to simplify the network using Thevenin Theorem.